black hole orbital decay as a mechanism for spiral arm formation in galaxies. This paper proposes a novel hypothesis for the formation of spiral arms in galaxies, suggesting that massive black holes spiraling toward galactic centers may be responsible for the observed spiral structures. Using the Whirlpool galaxy, M51, as a case study, since we observe the spiral arm takes one orbit to fall into the center, we calculate the drag coefficient required for a 10 solar mass black hole to complete exactly one orbit while falling from the galaxy's periphery to its center. Our calculations yield a drag coefficient of 5.31 to the 10th power kilogram per meter, producing a spiral trajectory that correlates with observed spiral arm morphology. This mechanism may also explain the observed correlation between galaxy mass and central supermassive black hole mass, as well as central bar structures in certain galaxies. Introduction. Spiral galaxies represent one of the most visually striking structures in our universe, yet the mechanisms behind their arm formation remain incompletely understood. Traditional explanations include density wave theory, stochastic self-propagating star formation, and tidal interactions. However, these theories face challenges in explaining the long-term stability and specific morphologies observed in many spiral galaxies. This paper examines an alternative hypothesis, that massive black holes spiraling inward toward galactic centers may contribute to or even generate the observed spiral arm structures. Since black holes cannot be directly observed in transit, their potential role in spiral arm formation may have been overlooked. We investigate this possibility through mathematical modeling of a black hole's orbital decay in a galactic environment. Here is our parameters and assumptions. We model a scenario involving the Whirlpool galaxy, M51, with the following parameters: black hole mass, 10 solar masses; galaxy mass, 10 to the 11th power solar masses; initial orbital radius, 40,000 light-years; gravitational constant g, Whewell calculation of drag coefficient for black hole orbital decay in M51. We determine the drag coefficient required for a 10 solar mass black hole to complete exactly one orbit before spiraling into the center of the Whirlpool galaxy, M51, due to dynamical friction. The calculated coefficient is 5.31 times 10 to the power of 7. Orbital velocity. The black hole's circular orbital velocity is, we use this equation, dynamical friction. Using Chandrasekhar's formula for dynamical friction equals 2. The black hole's circular orbital velocity is, we use v. For dynamical friction. Using Chandrasekhar's formula for dynamical friction FDF. For an isothermal sphere model, density approximation, with Coulomb logarithm where ln lambda is approximately 10, the dynamical friction force, FDIEF. Orbital decay analysis. The acceleration due to friction is a df, so the orbital period as t-orbit results. The calculated drag coefficient of 5.31 times 10 to the 7th power kilogram per meter. This would cause a 10 solar mass black hole to spiral from the galaxy's periphery to its center in exactly one orbit. Without drag, the orbital period would be approximately 402 million years. Discussion. The spiral trajectory generated by our model bears a striking resemblance to observed spiral arm structures in galaxies like M51. This suggests that black holes spiraling inward may play a role in spiral arm formation by gravitationally influencing surrounding gas and dust, causing material to concentrate along their path. This hypothesis may also explain several other observed galactic phenomena. The correlation between galaxy mass and central supermassive black hole mass. More massive galaxies would capture more black holes over time, building larger central black holes. Central bars in certain galaxies. These structures could result from the accumulated paths of multiple black holes spiraling into the galactic center. Conclusion. Our calculations demonstrate that a black hole with sufficient drag can trace a spiral trajectory that resembles observed galactic spiral arms. While the required drag coefficient is substantial and would necessitate interaction with a dense medium or other mechanisms, this hypothesis offers a new perspective on spiral arm formation. Future work should include more sophisticated models incorporating interactions between multiple spiraling black holes, the effects on surrounding gas and dust, and more detailed comparisons with observational data from various spiral galaxy morphologies. The physical interpretation of this extremely high coefficient indicates the scenario would require an extraordinarily dense medium that does not exist or some additional physical mechanism beyond standard dynamical friction. That could be due to the singularity interacting with the Higgs field. This simulation generated with an AI platform plugging the numbers in our scenario shows what this spiral trajectory follows exactly the spiral arm shape. Several interesting observations about this orbital decay. 1. The initial orbital velocity at 40,000 light-years from the center is approximately 187 kilometers per second. 2. Without drag, the black hole would take about 402 million years to complete one orbit. 3. With the calculated drag coefficient, the black hole completes exactly one spiral orbit in about 161 million years. 4. The orbit follows a spiral path where the radius decreases linearly with angular position. The simulation shows the dramatic effect of this strong drag force with the black hole following a beautiful spiral trajectory into the galactic center while completing exactly one 360-degree rotation.